This is the Materials for Sustainable Heat webinar. And so welcome. This is our April seminar. My name is Dr. Andy Smallbone. I'm an associate professor at Durham. And as you've probably seen on social media, and I'm sure you're all keenly locked in to this, it's Earth Day today, and a day how we can all take action to improve our impact on the climate and the planet. And we're delighted today to host two speakers who are exploring some potential answers for decarbonising our economy. This event is organised through the EPSRC Network Plus for the decarbonisation of heating and cooling, and it's part of a series which are looking at different challenges on decarbonising the heating and cooling sector. So we have two speakers who will present some of the latest outcomes from their projects. They are two projects out of the many that have been funded by the EPSRC's Decarbonisation and Heating and Cooling Programme. We have Dr. Yanan Zhang, who will talk about the fabrication and characterization of the innovative Vermiculite-Salt Hydrate composites for thermochemical energy storage. First, we'll hear from Dr. Zhang. And Dr. Zhang is a research fellow in Professor Su's team at Nottingham University and is funded through the ThermoStore EPSRC project. She undertook her PhD from 2016 to 2020 at Nottingham before joining Professor Su, and her research interests are sustainable energy technologies, energy storage, energy systems, and thermochemical energy technologies. Dr. Zhang, and you're ready to go, then please tell us all about the fabrication and characterization of innovative Vermiculite-Salt Hydrate composites for thermochemical energy storage.
Thank you very much. Thank you, Andrew. Good afternoon, everyone. Thank you very much all for coming today. I'm Yanan, and currently doing research fellow in the University of Nottingham. So the topic of my presentation today is fabrication and characterization of the innovative Vermiculite-Salt Hydrate composites for thermochemical energy storage. So when we talk about the energy storage, the first thing that comes to our mind is battery. Since the beginning of the time, people have been trying to store energy from various energy sources, so such as solar energy, wind energy, tidal energy, biomass energy, etc. But we don't have to store all our energy in the form of electricity. We can store them in their own way. This is also one of the part of my research. So in my presentation today, I will introduce these points, including a brief background information on energy storage, thermochemical energy storage, the TES composite preparation and selection, and the lab test and analysis of the TES composite. So first, let's talk about energy storage. What is the energy storage? So it is the capture of current energy for later use. And there are many kinds of energy, such as chemical energy, electrical energy, thermal energy, kinetic energy, and etc. So the history of energy storage has been actually a very long time. So back to about 4,000 years ago, the first ice house was built in Mesopotamia area. That was the first record people using energy storage. So in China, references that ice stored before 3,000 years ago. So in the year BC 450, an ice pot was built as a fridge. But at that time, it was expensive to build that one. So only when they were doing sacrifice or some important events, ice pot would be used at that time. And later in Tang Dynasty, the year of about 700 to 900, people started to use the saltpeter for cooling. That is kind of mineral rock with potassium nitrate or calcium nitrate that can absorb much heat when contact with water. Later in Qing Dynasty, ice ice house was very common at that time, and people can buy some ice cream with very reasonable price. So why today we still need to store ice and other energy? So of course, it is not only to achieve our ice cream freedom, but more importantly, to achieve the goal of low carbon and environmental protection. Today's cooling and heating will use a large amount of fossil fuels and generate large quantity of greenhouse gas. So look at the graph on the left. It shows that human activities are producing more and more greenhouse gas. Also, as you can see that the blue part at the bottom is energy supply, such as building heating and cooling. And this part accounts for the largest for the greenhouse gas emissions. Let's see the figure on the right side that shows the mismatch between the solar energy and the heating demand. We have a lot of solar radiation in summer or during the daytime, and this solar radiation produces a lot of heat, but in winter or at night, we need more energy to keep warm. So large carbon emission generated by the usage of fossil fuel to cool in summer and heat in winter. Our research topic is to use thermochemical energy storage technology to store heat in summer and release it in winter. This can greatly reduce energy waste and reduce carbon emissions and fill the mismatch between the energy supply and the demand. Okay, let's see the thermochemical energy storage. So thermochemical energy storage is the storage of energy in a reversible endothermic chemical reaction that stores different energies as chemical energy for use when we need it. It is different from the traditional batteries. If we store energy in batteries, we have to convert the energy into electricity that usually occurs at a very high temperature. The thermochemical energy storage is to convert thermal energy into chemical energy. So this process will have no complicated process. So the storage and the release of chemical energy are accomplished through chemical reactions. Look at the picture on the left side. When a compound is heated, it will be decomposed. So this process is usually an endothermic process because it takes extra energy to break the chemical bonds of the compound's molecules. So this process is called charging or regeneration process. The product of the decomposition of this compound is usually a solid and also a gas. When the product of the composition of this compound can be stored separately, and when we wanted to release the thermal energy, we can just directly remix the two parts, such as adding water or add the humid air to magnesium sulfate or calcium chloride. The two things then react when they come into contact and release lots of heat, which can be used for space heating. This reaction is usually an exothermic process, which is called the discharging or reaction in the thermochemical energy storage. However, in the thermochemical energy storage system, how should we prepare the composite as the TES materials? So in our thermochemical energy storage system, we need to choose the materials for heat storage depending on the heating demand and prepare the composite according to the choose matrix materials. So in this figure shows the preparation of the vermiculite-based salt hydrate composite. We need the following steps to prepare the thermochemical heat storage composite. First, we need to dry the vermiculite in the oven for at least 24 hours at a temperature of 150 degrees. At the same time, we mix the TES salt with pure distilled water using a magnet stir to make the saturate solution. Then mix the salt solution with the dried vermiculite and put the mixture at room temperature for at least 48 hours. Here, because of the low mechanical stress of the vermiculite, we need to be really slow and careful when mixing the vermiculite with the salt solution. After 48 hours, we need to put the composite in the oven at a temperature of 150 degrees for at least 24 hours. If the volume is too large, and also it will depend on the oven, the size of the oven you use, then it will need more time to dry it. So it's better to stir the composite every 6 to 8 hours to make sure that all the composite is dried well. After the composite is completely dried, we need to take the composite out of the oven and put it in a sealed container for cooling down to room temperature before we use it in the system. So how do we choose the TES salt? This usually depends on the energy density of the materials. For example, this figure shows the energy density of some energy storage materials. Usually we want to choose the energy storage material with the highest energy density. Also, we need to consider the regeneration temperature of the energy storage materials. Usually we don't want the regeneration temperature to be too high because a higher temperature means higher energy consumption in the charging process. But the regeneration temperature cannot be too low, as this will make the composite unstable and not good for long-term storage. So to measure the energy density and the regeneration temperature, normally we use a thermal analyzer in this process. So for the TES materials evaluation and selection, we prepare the different composite first. Then we use this thermal analyzer to analyze different composite energy density and the regeneration temperature. And this is the thermal analyzer used in our experiment, SDTQ600. So these 4 figures are the analysis results of the thermal analyzer. The temperature corresponding to the lowest point of the blue line is the regeneration temperature of the energy storage material. The average volume of the pink line in the figure in the target temperature range is the energy density of each material. So comparing these 4 pictures, these 4 material, we can see that the material in the first picture has the lowest regeneration temperature and the highest energy density. So this materials is vermiculite based mixed with magnesium sulfate and calcium chloride. So this one is more suitable as a heat storage material for thermochemical energy storage system. So this figure more clearly shows the energy density of different energy storage materials. In the following lab test, we mainly focus on the first 4 materials. These SEM photos show the changes in the surface of the vermiculite impregnated with different TES salt before and after treatment. We can see that the salt is attached to the surface of the vermiculite after the treatment. So later we do the sorption test of the materials in order to verify the water absorption of each material we choose and the optimum relative humidity level. We build up this experiment rig to measure the water adsorption properties of the 4 different TES materials we choose under different humidity conditions. So in this experiment, the 4 boxes provide 4 different humidity labels. We tested the 4 selected materials separately, and the testing time for each material is 7 days. We use load cells to record the weight change of the material under the different humidity levels. So let's see the figures. The figures show the weight changes of the 4 energy storage materials under different humidity conditions. Each graph shows materials. So from the 4 figures, we can see that the water adsorption property of these 4 materials are acceptable in a high humidity environment, but the water adsorption property of the material in the first figure are very good. It is still very good in a low humidity environment. So that means it will be easily to cause the deliquescence during the storage. So in the following lab testing, we will not use the first material. We choose the other 3 materials in the following test. So this is an initial rig that we use to test the energy storage capacity of the selected materials. The picture on the left is the test rig we built, and the picture on the right is the schematic diagram of the structure of this equipment. We can see that in the middle of the reaction body is a drawer to put the TES materials. And on the left side is a fan, and a heater and a humidifier are placed after the fan. So during the regeneration process, we turn on the heater and turn off the humidifier using the data logger and the PID controller to monitor and control the temperature. In this way, the hot air will heat up and dry the thermochemical energy storage materials we choose, and to release the moisture and store heat energy inside the materials. Then during the reaction process, we just turn off the heater and turn on the humidifier and let the moist air passing through the thermochemical energy storage material. Then the dried materials can react with water vapor and release heat. So we put some temperature sensors in the reaction chamber and put load cell to measure and record the weight change of the TES material. Thank you. So in this figure, the thermochemical energy storage material that based on the mixed magnesium sulfate and the calcium chloride, which is the 3rd one, shows the best performance because of its low regeneration temperature. And also in the reaction process, the outlet air temperature is 46 degrees. So that is ideally suitable for space heating. In some later tests, we also found that this heating state is very stable compared to other thermochemical energy storage materials. And after several energy storage and release cycles, its heating effect is still very good. So these properties indicate that this material is a good thermochemical energy storage material, and it is also feasible in the real application. So this one is the conclusion part. In this presentation, thermochemical energy storage and the TES materials has been introduced. The detailed steps of TES materials preparation have been described. Then through some experiments and some lab tests, we found that the thermochemical energy storage composite of vermiculite with magnesium sulfate and the calcium chloride has the highest energy density and the lowest regeneration temperature compared to other test materials. And the space heating temperature can be as high as 46 degrees, which is feasible for practical application. So in the future work, we will build a prototype to analyze the application of vermiculite with magnesium sulfate and calcium chloride in a real building environment, and analyze the life cycle of this material. Thank you very much.
Thank you, Yanan. Thank you very much.